Can people hear me okay? Okay, great. Thank you all so much for being here, and thank you to the organizers. This talk includes some joint work with Eleanor McSpirit, and it's based on these two papers. So just as an overview, the focus of this talk is going to be a recently developed family of two variable series invariants of a certain infinite family of three manifolds. These were developed by Akhmachet, Johnson, and Krushkal in 2022. And these families have these two properties where they encode all SU2 quantum invariants of the manifolds on which they're defined, and I'll say more about what that means momentarily. And they have connections with lattice and Heggard-Floer homology. So the results covered in this talk is that we calculate these TQ series for infinite families of three manifolds. This is a relatively young invariant, and as far as we know, we provide the first calculation for an infinite family. We also use this calculation to establish number-theoretic properties of these invariants and radial limits towards roots of unity. And these radial limits give rise to even more new invariants. So I'll talk more about what those are. But I'll start by saying a little bit more about what I mean by SU2 quantum invariants. And when I think of SU2 quantum invariants, I start with the Jones polynomial. So this is an invariant of oriented links. If you have such a link in the three-sphere, you choose a diagram. And we can calculate the Jones polynomial as these two quantities that each independently depend on a choice of diagram, but when we put them together, everything cancels out, and the resulting polynomial is invariant of the diagram. So we have this A power that has to do with a signed count of crossings, and that, of course, depends on the diagram. And then we calculate the Kaufman bracket polynomial of the diagram D according to these rules. So you'll have some picture with some crossings. First, you can use the third rule to eliminate all the crossings and get a linear combination of crossingless closed curves, so just a bunch of circles. And then you can use rules 2 and 1 to actually evaluate each diagram of circles and end up with a polynomial in A. And if you'd like, you can change it to a polynomial in T. So these SU2 quantum invariants are now invariants of three manifolds. I will sometimes call them, as they are often called, the Witten-Reshetikhin-Turayev, or WRT invariants. These are indexed by roots of unity. So if you fix a manifold and you choose a specific root of unity, these invariants give you a complex number associated to that pair. Now, these invariants were formulated by Witten in physics terms, and then they were made mathematically precise by Reshetikhin and Turayev. And this mathematical setup involves representations of quantum groups. However, there's also this nice combinatorial formulation in terms of the Kaufman bracket, and this is due to licorice. So in some sense, you could think of these as an upgrade of the Jones polynomial, an invariant of links, to this invariant of three manifolds, which we know can be built from links. So there's this result of Licorice and Wallace that every closed, oriented, connected three manifold can be obtained from surgery along a framed link L in the three-sphere. So sometimes we call this framed link L a surgery presentation. And what you can do is you can start with a surgery presentation. If you'd like to calculate the WRT invariance, I should say, you start with that surgery presentation. And then you're going to calculate the Kaufman bracket of a collection of links obtained from L. And then once you have that, you're going to have this massive polynomial-looking thing, and you'll evaluate that at various roots of unity, and that's going to give you your invariant of the pair manifold root of unity. So now I want to talk about this program of unification of the SU2 quantum invariants. So you can think of all these invariants as living on the unit circle. Since you have one for each root of unity, you have like a infinite points worth on the unit circle worth of invariants for each manifold. But in 1999, Lawrence and Zagia came up with this series A of Q, and it was specifically for the Poincare homology sphere, sigma 235. Thank you. And this series had the property that it encoded all of these WRT invariants via radial limits. So they defined this holomorphic function on the unit disk, which it's not coming through super clear, at least to my eyes on the slides, but this is like shaded in a very light blue. And as you take a limit towards any one of these roots of unity along this ray coming out from 0, you're going to get a renormalization of the Witten-Reshetikhin-Turayev invariant of that manifold. So how did they come up with this series, or how did they define it? So they have this chi-plus function that comes from number theory in a certain sense, where you just look at congruence mod 60. It either takes the value of +1, -1, or 0. And then you have these powers of Q. So chi plus of n times q to the n minus 1 squared over 120, and you take the sum from 1 to infinity. Magically, this is a holomorphic function. It converges on the interior of the unit disk, and all of our radial limits tell us the Witten-Reschke-Derive invariance of that specific manifold. Actually, maybe I'll stop here and see if there are questions. Okay. So I mentioned some of the nice properties of this thing already. It's a holomorphic function on the interior of the unit disk. It recovers WRT invariance via radial limits. It was also found by these two authors to satisfy interesting transformation laws. And these transformation laws motivated Zagier's definition of a quantum modular form, which has since become an object of great interest to number theorists. So now we'll do a quick detour to talk about modular and quantum modular forms, like a topologist's introduction to them. So while I'm doing this, I'd like for us to keep in mind this map that sends tau in the upper half plane to q to the e to the 2 pi, to q, which is equal to e to the 2 pi I tau. So it's going to wrap the upper half plane into the unit circle. And notably, the rational numbers are going to become roots of unity. So sometimes we'll go back and forth between talking about the upper half plane and the unit disk. So a modular form has to do with the action of SL2Z on the upper half plane. So if you have some matrix gamma, you can send your tau to A tau plus B over C tau plus D, where A, B, C, D are the entries in this matrix. And a modular function would just be a holomorphic function that is invariant under every gamma in that group. So f of gamma tau is always equal to f of tau. So SL2Z contains a lot of things. There's like dilations and translations in here. So being invariant under all of those things is a really like restrictive condition. And you can do some complex analysis to show that these functions are like pretty limited in what they can be. But modular forms are objects that have this less perfect transformation law. So now we have a less restrictive condition. We can have more things. Specifically, rather than requiring f of gamma tau is equal to f of tau, we now require that f of gamma tau is f of tau multiplied by some quantity that depends on gamma. So this c tau plus d comes from the matrix to the power of some k plus some other technical conditions that I won't get into, but we call k the weight of f. So a modular form of a weight like k means that this equation holds for all gamma in SL2Z. So basically, we can think of modular forms just as holomorphic functions on the upper half plane, which behave in a particularly nice way with respect to a group action. They sort of grow predictably as we act by some gamma. So now we'll talk about quantum modular forms. So this is, I'm sort of giving a definition for the purpose of this talk. The field of quantum modular forms is vast, and I'm not claiming to summarize the entire field. But for our purposes and our setup, we're going to look at a function on the upper half plane that's holomorphic, and we're going to focus on limiting values toward rational points. So we'll be sort of looking at, we'll be taking the limit in like vertical lines towards all of these rational points. And we're going to say that f is a quantum modular form if at all but finitely many of those rational points, those limits don't obey the modularity condition, but they have an obstruction to modularity, which extends to some nice function. So here the obstruction to modularity is defined in this way. It's called h gamma of tau, and there's one for each gamma. Now, in the modular form setting, h gamma would be identically equal to 0 because we require that this is like equal to positive this or something like that. So we have some obstruction, and we just mandate that the obstruction is reasonably nice. Now, nice means different things in different contexts. This definition was sort of built to encompass a lot of examples following a similar pattern but occurring in like disparate fields of study. So in our case, nice is going to mean real analytic, but there are examples where nice can mean something else. So really, we can think of this as some function in the upper half plane, and we don't really care if the in the upper half plane, we don't really care if it's modular or not. We don't super care what's going on there. We care what's happening in the limiting values towards roots of unity, and we want to have an obstruction to modularity that is reasonable. So before I return back to AQ, are there any questions? All right. So A of Q is the series of Lorentz and Zagier unifies the Witten-Reschetiko-Tariv invariance of the Poincare homology sphere via radial limits. We now know that it is a quantum modular form. This is also a result of Lorentz and Zage. And it's a holomorphic function on the interior of the unit disk. So one of the big questions people had was, can we extend this to other 3 manifolds? Can we find such a series for other 3 manifolds? And so this is where the Z-hat series comes in. This is work of Gukov, Pei, Putrov, and Vafa. And they extend this series now to an invariant of a family of manifolds called negative definite plumbed with spin C structures. I'll say more about what I mean by negative definite plumbed momentarily. But the Z-hat invariant associates to each such pair a Q series that defines a holomorphic function on the interior of the unit disk, like before. Now, the authors conceptualize this as the Euler characteristic of this physically defined but not yet mathematically defined homology theory. And they situate all of this within a physical framework. And this motivates the expectation that there should be a mathematical formulation for Z-hat for all 3 manifolds rather than just negative definite plumbed. And the program of extending this is work of some people in this room. Z-hat is also maybe expected to play a role in categorification of WRT invariants since it's arising as this graded Euler characteristic of this object that we maybe don't understand mathematically yet, but understand physically. And it was shown that the Z-hat invariant does indeed unify the Witten-Reschetiko-Tariv invariance of all manifolds on which it is mathematically defined, and this is a result of Murakami. So we do now have these Q series associated to each negative definite plumbed 3 manifold with the choice of spin C structure that, in a precise sense, do what we want them to do. They unify the invariants and they define holomorphic functions. They're not always modular forms, but they are quantum modular forms, but they are for vast families of 3 manifolds. I should also mention work by these 2 groups of authors, a few of which are in this room, provides this theoretical framework illustrating how this Z-hat invariant sort of sits in the intersection of topology, physics, and number theory, and how questions about Z-hat can sort of illuminate connections between these 3 fields. So now I'd like to talk about, oh yes. Yes. Sorry, can you rephrase the question? I don't think it recovers a known invariant, but yeah, I'm glad you mentioned that because it's on this slide. So a lot of great work has been done, more than is on this slide. This is not a complete summary. But I'm going to talk about some of the extensions and some ongoing work that has to do with the Z-hat invariant. So modularity properties for infinite families of manifolds have been established. And I say modularity properties because it's not always straightforward quantum modularity. Sometimes it's something called higher depth modularity. There's a series for knot complements, which leads to a gluing formula and a surgery formula. The surgery formula doesn't work for any given surgery presentation. But the hope is that this could be a first hint at a more general formula that works for any 3 manifold. There's also higher rank series. So we can think of the Z-hat invariant as associated to the A1 Lie algebra. And work has been done to define analogous series for other Lie algebras. The minimal exponent of this Q series gives rise to something called the delta invariant, which has been studied by some authors in this room. There is a calculation for all Seifert manifolds of the Z-hat series, and this is called the reduction theorem of Gukov, Kotsarkov, and Svoboda. And this is something that I really use, and it inspires a lot of the results in this talk, so these authors deserve a lot of credit. And there's also a 2-variable refinement between the Z-hat series and lattice homology. So both Z-hat and lattice homology are invariants of negative definite plumbed 3 manifolds with spin C structures. And these 3 authors figured out a new invariant that encodes both of them, and I'll talk about that now. So this is the TQ series invariant, Z-hat hat, that I mentioned earlier of Akhmetshed, Johnson, and Krushkol. I'll sometimes abbreviate that as AJK. And this is for negative definite plumbed 3 manifolds with spin C structures like before, and they define it using lattice homology. So this is a theory defined by Nemethy, and its equivalence in a certain sense with Higard-Floor was shown by Zemke. And what they do is, in lattice homology, there's this combinatorial object called a graded root, which encodes the 0th lattice homology. And these authors add what they call weights to the graded root, and they make something that I think is really fun to say, which is weighted graded root. It just kind of rolls off the tongue. And so they use these weighted graded roots to extract a two-variable series. And the two-variable series has the property that when the first t variable is set equal to 1, we recover the z hat invariant, which we know. But for all these other values of t, things like modularity properties and radial limits hadn't really yet been explored. So this talk is going to discuss some of the results on those two things, modularity properties and radial limits, for other values of t besides 1. So now I get to tell you what negative definite plumb 3 manifolds are. So given a plumbing graph, we have this tree with integer weighted vertices. And what we can do is we can build a framed link, which I'll call L of gamma, where you take each vertex and you have an unknot with framing equal to the weight of the vertex. And then whenever two vertices are connected by an edge, you link those unknots together like so. And so this is the surgery presentation for a 3-manifold now, because we have a framed link in the 3-sphere. So that's great. So this graph here really tells us, in fact, how to build a 3-manifold, Y3 of gamma. Now, Y3 of gamma bounds some manifold X4. We can define X4 to be the 4-ball with 2 handles attached along this link. And Y3 of gamma is the boundary of X4. X4 has an intersection form. It could be positive definite, it could be negative definite, it could be something else. And so we're going to say that a 3-manifold Y is negative definite if it's homeomorphic to Y of gamma for some gamma, and that associated Y of gamma, we associate to it that X, and that X's intersection form QX is negative definite. So if the plumbing graph gives rise to a negative definite 4-manifold, then we say that Y of gamma is negative definite, or any manifold that is homeomorphic to it. So I mentioned earlier that these TQ series are invariants of a pair Y3K, for K a spin C structure on Y. We're always going to be working with rational homology spheres, and in fact, we're going to start by working with a series that no longer depends on a choice of spin C structures. So you can take a finite sum over all spin C structures and get a new series, which is denoted z hat hat sub 0. And the rest of this presentation covers only these sums, so we're just going to drop the 0 subscript. And we're going to always assume that we're working with the non-spin C dependent version. So Seifert manifolds, for the purposes of this talk, they're an infinite family of negative definite plumb 3 manifolds specified by this set of data. So you have some B and you have K ordered pairs, AI, BI. They have to satisfy some certain conditions, and we refer to this tuple as the Seifert data, and we call K the number of exceptional fibers. So just as a summary of our results, we're going to calculate the TQ series for Seifert manifolds, and then we're going to specialize T to be some root of unity zeta, and we're going to focus on the case of 3 exceptional fibers. We're going to show that the resulting 1-variable series are up to normalization quantum modular forms, and that radial limits toward roots of unity exist and can be thought of as a novel infinite family of zeta-deformed Witten-Reshetikhin-Turaev invariants. So this is a result on the z hat hat series. So turns out that if you have your Seifert data, you can actually calculate the z hat hat series rather than building a weighted graded root and taking your limit. You can calculate it just from the Seifert data in the following way. So all of the highlighted quantities here are determined by the Seifert data, by this tuple in some way. So you start by building a rational function in 2 variables, f0. Then you take that rational function and you build a formal power series from it. And this is going to have infinite positive exponents and infinite negative exponents. It's not going to be something we can make sense of as anything beyond just a formal power series. But we can do something to it, manipulate it in a certain way, which is a Laplace transform. And that's going to give us something that actually converges. So wherever we see z to the n, we replace it with q to the n squared over 4a, where a comes from the Seifert data. So again, somehow we're taking all of the negative exponents and folding them over to the positive side, and the way in which we do this gives us now something that converges on the interior of the unit disk and for any fixed t in the complex numbers. The last thing we have to do is renormalize by this rational power of q, and now we get the z hat hat series in t squared. And so we can put it all together to write it like this. Basically, this is a series of steps that at every point really only depends on the Seifert data. And this is an extension of the work of Gukov, Katsarkov, and Svoboda's reduction theorem for the 1-variable z hat series. So again, I think these authors deserve a lot of credit. And it also builds on previous calculations for Brieskorn homology spheres by myself and Eleanor McSpirit. And this formula is what we use to establish modularity properties and radial limits of the TQ series. So first I'll talk about radial limits, because we actually need radial limits to be able to think about modularity the way that we want to. So if we fix a manifold with now 3 exceptional fibers, and we fix T to be a root of unity zeta, you can take a limit along a ray from the origin to any root of unity, just like a straight line. And these limits are always going to exist, and they can be thought of as zeta deformed Witten-Rescheteken-Terive invariants. And the reason we say that is because when zeta is 1, you recover the usual Witten-Rescheteken-Terive invariants. And that was already known. That's the result of Murakami in our context. So here, zeta is like our fixed value of T, and then C is the root of unity that we're taking the limit towards. So like one of these roots of unity is like fixed, and one of them we're varying. So this concerns like special values of T, but I'm also interested to understand what happens for a general T, and what that might tell us about the role of T in this invariant. So when M is as above, we know that if we let Q go to 1 for any value of T, so now we're just looking along the ray from 0 to 1, we get T plus T inverse minus 2. So this is kind of, I don't want to say strange, but somehow in this invariant, as Q goes to 1, you're like forgetting all the Seifert data. Like all the Seifert manifolds are going to have the same invariant for the same T. So it's not that exciting in terms of detection or anything, but it's exciting, well, maybe not exciting, but it's informative to me because it gives me a glimpse of like how the T variable can affect things. So now I'll talk about quantum modularity for k equal to 3. So again, we fix T to be a root of unity, and we let M be a Seifert manifold with 3 exceptional fibers. Then z hat hat of zeta q is equal to a rational power of q times a polynomial that comes from the Seifert data plus a quantum modular form of weight 1/2. So building on results about the z hat series, we showed that the z hat hat series, when T is a root of unity for 3 exceptional fibers, also enjoys similar modularity properties. And the proof idea here is that we think of the z hat hat series as a Q series with Laurent polynomial coefficients in T. And then when we do that, we find that the objects we're working with have these symmetries. Well, actually, we can decompose it into a sum of objects that have nice symmetries that allow us to use work of number theorists. Oh, thank you. And so when we do this, we can apply a known framework of Brinkman and Roland to realize this Q series as an Eichler integral of a cusp form. So just as a summary, we're working with this recently developed TQ series that provides a common refinement with the z-hat and lattice homology. We know that z-hat has interesting modularity properties and radial limits, and we were curious what happens with z-hat hat. So we calculated the TQ series for an infinite family of 3 manifolds, and then using that calculation, we showed that you get modularity when k is 3 and t is a root of unity. And we show that radial limits in this case give rise to a novel family of deformed SU2 quantum invariants. And so current and future work, one of the things I'd like to do is actually understand how this decomposes over different spin C structures. So I'm looking at the sum over all spin C structures right now, but I'd like to know, how that sum breaks up. I'd also like to extend calculations, limits, and modularity results to higher rank series defined by Park. So Park has a z-hat, excuse me, a z-hat series for A1. Lastly, I'd like to just calculate more radial limits because I'd like to get a topological understanding of these zeta deformations and what they mean. Thank you. Yeah. I do not, but I think that Gukov, Katsarkov, and Svoboda do. So Joseph, do you have any comments?
Yeah, that was sort of like the original motivation of looking at this, but I would say we don't know.
So you have the statement about quantum polarity for T when you set T to be a root of unity. So the statement this is a vector valued kind of vector quantum module, right?
We realize it as, I'm actually not quite sure. We show that it is an Eichler integral of a cusp form of weight 3/2. And so we have our series, and then we say, okay, this is the thing that we think it should be an Eichler integral of. So we build a cusp form, and then we show that when you take the Eichler integral of that cusp form, you get back the same thing. I'm not, I mean, maybe the framework of Brinkman and Roland does have some vector-valued modularity under the hood, but it's not something that we're thinking about. Oh, yeah. So the number of terms in our sum grows as the order of the root of unity grows. And each of those is a false theta function. And then we pass to a certain subgroup to get that they're going to all transform as one. The D invariant can be seen through the graded root has the D invariant in it. So in the sense, like, you can get the D invariant. But I don't know how to see the D invariant in the series itself, because the series is sort of this limit of the graded root where you're sort of forgetting which terms I picked up from which grading. And it's like a sum over all the gradings.